Welcome to AP Podcast 14.7. This is on polyprotic acids, and all that means is more than one proton. So if you think about something like sulfuric acid, right, it's going to dissociate like this. And then HSO4 minus. Now, what that means is when HSO4 minus is floating around, okay, it can also lose another H and just have the sulfate ion floating around. All right? So it's got more than one proton to disassociate. Now, the important things about this is that first H is going to come off much easier than the second, for reasons I'll show you in just a second. And if you look at the KAs for each one of these, the KA for the first step is much bigger than for the second, which is kind of redundant if you think about this sentence right here. And so you'll note these KAs as KA1, KA2, KA3. So let me show you an example. Here's carbonic acid, and you can see the first dissociation where it breaks up into the hydrogen carbonate and the hydronium ion. And look at the Ka. It's 1 times 10 to the minus 7th, which I think you would agree with me is a very small number. And of course, this is a weak acid, right? And we're talking about weak acids in almost all these situations. Now, this is floating around in solution, and that H can break up, all right, into this reaction. But look at the Ka for this, right? Now, minus 7th to the minus 11th is 1,000 times, right? Or actually, it's 10,000 times. So we're talking about a massive lower amount of dissociation occurring with this second H. And so really, if you think about calculating the pH for something like this, remember when we had two weak acids, we found the pH with the first Ka and we ignored the pH with the second one because it was so small. And effectively, we can do that. It's really not going to be a big deal. So really, it's that first one that's going to matter the most. But you might see a question once in a while that when they want you to actually figure out each dissociation. Okay, but most of the time, we are going to go ahead and ignore that second one. Now, here's a question that we got right from our book, where they want you to calculate the pH of the 5 molar phosphoric acid solution and the equilibrium concentration of each species. Let me just say that this problem is rather long and involved, and if it's something that you would want to see, it's definitely in your textbook. But instead of me doing the problem, I'm just going to show you the H plus concentration that comes off of each one. So with this first dissociation, we get the H plus equaling 0.19 molar, which is pretty significant, and that'll definitely affect the pH, right? But now when we take basically the H2PO4 minus dihydrogen phosphate, and that goes through its dissociation, and that's what this Ka2 is, the H plus concentration that we get from that is 6.2 times 10 to the negative 8th molar, which is incredibly small compared to that one. And then if we want to even go ahead and take the third one, and that's when you have hydrogen phosphate, okay, when that disassociates with this Ka, we get an H plus concentration equaling 1.6 times 10 to the minus 19th. Now, if we were to add these all up, obviously this number right here would do nothing. You would add that to that and get nothing. And you could even say the same thing for both of these. I mean, think about these two numbers right here. If I were just to add them up, 0.19 and this other number of 0.1, 2, 3, 4, 5, 6, 7, 6, 2, right? All right, I add those up. Effectively, what do I get? Okay, so that's the important part about what's going on in a polyprotic acid. That second or third dissociation in this situation is so insignificant as far as how it's going to affect the pH that you can effectively ignore it. All right? Except, as I say that, let's talk about sulfuric acid, because sulfuric acid is special. And The first step, it's a strong acid, right? So for example, if I said you had, well, let's just look down here. Calculate the pH in a 1 molar solution of sulfuric acid, right? If I had 1 molar sulfuric acid, I would get 1.0 molar H plus. Why? Well, because it's one of our strong acids. We know that. Okay? But look at this Ka for step 2. And when we say for second step, we're talking about hydrogen sulfate dissociating into, of course, H plus and sulfate, right? Okay, look at that. That's not that small. Okay, it's 0.012. And as far as weak acids go, you guys are used to seeing Kas that are really small to the -5, 6, 7, and beyond. That's pretty big. So it turns out that in some instances, we have to actually worry about that. All right, so what happens though is when we get a very dilute concentration of sulfuric acid, something like this, 0.01 molar, that Ka starts to play a bigger role. I'm not saying you're going to see this very often, but it's just something we need to be aware of, that in dilute solutions, that second dissociation is going to play a bigger role. So what I'd like to do is just kind of show you how it does play a bigger role. So here's the reaction. Now let's just set up a simple ice chart. All right, so initially I had a 0.1 mole. This is the second dissociation, right? So remember, when sulfuric acid dissociated, right? Strong acid, we had 0.01 molar. We had 0.01 molar of H plus, right? Because it is a strong acid. So we had this, 0.01 molar of that. But we also have this, 0.01 molar of that. And then we have none of this, okay? So that's what I have initially. Now, what's the change going to be? Well, we're going to lose some X. Would you agree, hopefully? We're going to gain some X. But really, what are we gaining? Well, we're really gaining, oh, pardon me, let me finish this off. And we're going to gain some X there. So then at equilibrium, what I've done is I've got 0.01 minus X. And then here I have 0.01 plus X. And then I have X. So I've got my chart. So let's go ahead and write out this equilibrium expression. All right, so my Ka equals 0.012, right? And that equals 0.01 plus X times X over 0.01 minus X. Now, like always, this is a weak acid problem, so what we're going to do is we're going to make the assumption that this little X right here is insignificant, so we're going to go ahead and ignore it. And then when we solve for X in this situation, and again we're solving for this one right here, we get an answer of, let's see, I've got it right here, 0.012. Okay. Now look at that answer. Is that ridiculous or what? We're saying the X concentration, or in this case, how much H is going to come off, is bigger than what we started out with. All right. So that tells us that we've got to use a quadratic equation to solve this problem, and we're not going to do that this year, which is kind of nice. But the important thing, the thing that's the concept that we have to get in our brain is when you have a diluted solution like that second H dissociating, it's going to play a bigger role, that Ka. So we've got to be aware of it. You won't ever have to calculate it out, but the important thing is that you have to understand that concept. Okay? First H comes off, strong acid, no problem. Second H, it's a big deal if it's a dilute solution. So something to keep in mind, something that might pop out. It's a really good multiple choice type question. All right. So there you go. Hopefully this stuff made a little more sense to you, and we'll see you next time.